Comments on the following video. The place. It's room 55 on the ground floor of the building Cannizzaro, which is the oldest building of the Department of Chemistry of the University of Rome La Sapienza. The spaces. Room 55 is large and is divided into 3 rooms of different sizes. For convenience, we indicate room A was the larger one, but which was not fully used for the experiment. Room B, on the ground floor, is about 1/3 the size of A and has a ceiling height of about half that of A, in any case greater than 2 meters. Here all the hardware part of the experiment had been developed. Room C is above B. Here the entire control and acquisition part of the experiment was developed. It has a slightly smaller surface area than B, and the height of its ceiling added to that of B is approximately equal to the ceiling of A. C is reached by stairway starting inside A. The registration. It was made on April 2, 1995, Sunday, by myself. Total assembly had been completed a few days ago, and a series of control tests had begun. The quality of the video is not excellent, but there is more than one explanation. If I remember correctly, at that time digital cameras weren't available yet, and in any case, I had a cassette tape camera which I bought in New York in 1993. In the video you can see, room C, that the monitors of the 3 computers in operation are inserted in a metal box made of mu metal, material which shields the magnetic field. The monitors of that time were cathode ray tubes. As is known, the trajectory of electron is influenced by the magnetic field. An nuclear magnetic resonance spectrometer equipped with a powerful superconducting magnet in liquid helium was in operation in the adjacent laboratory. The lines of force of that field partly entered our laboratory. That Sunday, I realized that my camera was also affected by the field, and therefore I was forced to shoot looking for the position of the minimum interaction. The noises. There are mainly of 2 species. Room B is dominated by the combined continuous noise of the rotary pumps and the turbomolecular pump of the mass spectrometer, as well as periodic noises of a various actuator. In room C, predominantly the acoustic of cosmic neutron counting and the instrumental beeps. Bearing in mind the description of the laboratory previously made, here we are in room A, and the first shot concerns the rack cabinet where all the control electronics of the neutron detector are contained. An interface then starts from here which connects the data acquisition to the upper floor. The more detailed description of the neutron detector is reported in an article whose references are cited at the end of video 8. Instead, room B can be glimpsed, where a large white cylinder is visible. It's the neutron detector inside which is all the experimentation. Here it is. There is a tangle of wires covering the vision of 4 cells. This white space where you see this circumference inside which are contained 6 stainless steel tubes containing helium-3. They are neutron counters with a central electrode at 1000 volts with respect to the stainless steel tube. These 4 stainless steel cylinders, each of which contains a catalytic recombiner of the deuterium oxygen mixture, here the recombinant EV water is collected and then subsequently analyzed for the presence of tritium. Then follows the gas line coming from each cell. Here the entire gas sampling apparatus is visible, which consists of an automatic system controlled by one of the computers to divert the gas flow of the cell under examination to the sampling. The visible stainless steel cylinders have a volume of 150 cubic centimeters. The collected volume is diverted to a stainless steel container filled with size getters alloys and subsequently to another stainless steel container with activated carbon and in liquid nitrogen, as visible in the blue dewar. The function of these 2 stages is to drastically reduce the deuterium content to make possible the determination by mass spectrometry of helium-4, especially if in trace amounts. As seen previously, the mass spectrometric separation of deuterium by helium is critical. The introduction of gas into the mass spectrometer is regulated by a low vacuum system such as to create the optimal working conditions in the spectrometer chamber. Upon command, the opening of the inlet needle valve into the spectrometer. The spectrometer chamber always works around a pressure of 10 to minus 9 millibar. The pressure gauge inside the chamber controls the closure of a needle valve if the pressure rises above a preset value. It can be observed that all the connections are made with Swagelok pipes to ensure. In addition, we are now upstairs in room C. Here you see some power supplier. It is the rack cabinet on the left there. Are various instruments that it would take too long to describe individually. The most important one is the data logger, which is this one. It can capture up to 60 analog channels and a further 30 digital input channels. There are other ancillary instruments such as this one, for example, which is a counter of the charge that passes through the cells during electrolysis. I remember that the electrolysis takes place in galvanostatic conditions and the current is varied during the long experiment. This is to verify the efficiency of the electrolysis in relation to the consumption of EV water. Some of the instruments present are of our own design and homemade. Below there is a rotary stills recorder that records the temperature of the 4-cylinder heating system of the recombiner you have seen before. The first computer you see is a Macintosh FX running on a program made with LabVIEW. The assigned function is to acquire the shape of the pulse associated with each neutron detected by the neutron counter through the connection with the digital oscilloscope that you see. This is another Macintosh FX that also runs with a LabVIEW program for acquiring all the parameters of the cells in the experiment and controlling a number of functions. All this takes place through the connection via interface with the data logger. The data logger controls the maintenance of the electrolyte level in each cell through the laser beam level sensor. Another important control is the rotation speed of the pump, which ensures the constant flow of thermostated water in each cell. The accuracy of flow calorimetry depends greatly on this. These beeps you hear periodically are nothing more than the signal that the neutron count has detected. The display you see on the wall shows the neutron counts of the 12 groups of a counter, each consisting of 5 tubes of helium-3 at 6 bar. They are in fact 60. Inside the toroid, where the cells are arranged, there is a camera in the central part that rotates and can go and check the immersed part of the cells. This is the third computer. It's not a Macintosh that is directly connected to the mass spectrometer with a spectrum acquisition system. As has been described, the acquisition of the signal takes place with the multiple ion detection mode, that is multiple ion detection, in which we are able to detect the intensities of the selected ion species as a function of time. I remind you that the choice that has been made is to select, in addition to the deuterium, the valley between deuterium and helium and the neon 2+, because these are parameters that make it possible to check that the presence of helium does not derive from contamination from air. And here you see that the sampling has taken place right now. You can see that the pressure has suddenly risen because practically gas has entered the mass spectrometer. The small flow of gas that enters changes the pressure inside the spectrometer. After that, as the gas is pumped, the signal decreases. The signals that are required are represented as you can see. Some are signals that are the masses. The last three refer to the pressures, both within the spectrometer chamber and within the low pressure deuterium abatement system. Provisional conclusions on May 2023. It was an exciting experience that unfortunately did not produce definitive results. However, they demonstrate serious experimental evidences that cannot be sufficiently archived as experimental artifacts. Years later, the situation has not substantially changed despite the numerous international experimental confirmations of both excess heat and the nuclear phenomena. Reproducibility is still an issue. None of the proposed theories satisfactorily explains the nature and the diversity of the observed phenomena. Are low-energy nuclear reactions real? Are they acceptable according to current knowledge? New roads seem to be on the horizon. Like so many other stories of scientific research, to which time has since given answers, even the understanding of nuclear phenomena in condensed matter does not seem to be mature yet. Is cold fusion alive yet? Here is the whole list of international conferences on cold fusion starting from 1990 up to the present day. In fact, the next one will be in August 2023 in Poland. Judging from this list, it would seem that cold fusion has had a continuity over the years, and there is still many researchers who continue to work on it. All this suggests that this field is still alive.